1, 0, 1, 1, 0, 1, 0. Let's say that I had, oh, let's see, 1, 0, 1, 1, 0, 0. I need another one. So let's suppose that was my number in binary. Binary means you can only use zeros and ones. Okay? So then what you're going to want to do then is figure out what that value actually is. So in a computer, that's how the computer stores it, but that's not how we think of it. It's actually a number that means something to us, but we have to understand how this works first. So I'm going to actually go over to, this is in binary. I'm going to go over here and I'm going to do something with a decimal number. So like, let's say the number 4,271. So what this really means is 170, 200. No, you're fine. Okay, so this is the thousands place, the hundreds place, the tens place. So this is really the same as this. Okay, it's just faster to write that way. And then this would be the ones place, or 10 to the zeros place. Anything to the 0 power is 1. This would be the tens place, so 10 to the first. This would be the hundreds place, so 10 squared, 10 to the third. Okay, well, just like how the decimal system works, binary works the same way. It's just that instead of the base being 10, it's 2. So like this would be 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3. I'm going to run out of space here. 2 to the 4, 2 to the 5th, 2 to the 6th, and 2 to the 7th. And this is how binary gets represented in a normal computer, because in a normal computer, 1 byte is 8 bits. So there's 8 ons and offs. So in a computer, this would be like electricity on, electricity off kind of thing in the memory chip. So then I can figure out what this number is by looking at what I have. So 1 times 1, well, that's a 1. 0 times 2, well, that's nothing. What's 2 squared? So then 1 times 4 would be 4. So I'm going to add a 4 in there. No 2 cubed. There is a 2 to the 4th. So 16. Okay. And then there is a 2 to the 5th. So 32. And then no 2 to the 6th. And then 1 2 to the 7th, which that one's a bigger one. And it's 128. I'll just tell you that right now. Okay. Because we skipped 64. So then this is the value of that number. If we add all those up, 128 plus 32, well, let's see, 2 and 28 is 30, so 160, 176, 180, 181. So this is really the same as the value 181 in the decimal system. So that's how you convert binary to decimal. So the thing is, those are really hard to write. Like in when we work with color, for instance, color is actually a 6-byte piece of information. Do you remember things that look like 3A, B, 2, 6, F, or something like that? Okay, so that's what we're actually going into. This is how a color gets represented in web design. This right here is 6 pieces of information. It's actually 3 bytes because it turns out that these two together makes 1 byte, these two together makes 1 byte, etc., etc. But that's a lot of. If I was to write 3 bytes here, that would, you'd multiply this by 3, you'd have 24 digits that you'd have to write down for binary. And we don't like that. So what we do is we take binary and we convert it to what's called hexadecimal. And hexadecimal is based on 16. So like if I write a number in hex, so hexadecimal, if I write a number in hexadecimal, then let's say I had the number 7C. Well, C, the numbers 0 through 9 mean exactly what they sound like. So 0 to 9 are exactly what you think. Then A would be 10, B would be 11, C is 12, D is 13, E is 14, and F is the same as 15. Because hexadecimal is base 16, so you have to have 16 different values. So 0 to 15 is 16 different values. So then this is the 16 to the 0 place, and this is the 16 to the first place. And so this means 16 to the 0 is what? 1. So it's 1 times C, and C is 12. So that means I have a 12, and then I have 7 16s. So I'd multiply 7 times 16, and whatever that number comes out to be, and that one is hard for me to do in my head, so I'm just going to cheat a little bit here. 112, okay? So 7 times 16 is 112 plus 12, which is 124. So then this means 124. Notice that this number is way smaller than this number in terms of how many digits you have to write, even though the number of values are actually pretty similar. Now, it turns out you can actually convert binary to hexadecimal really easily, because if you look carefully, the first 4 digits of binary, 0, 1, 2, 3, well, 2 to the third is 8, and the next digit would be 16. If you add all of these up from, so 8 plus 4 plus 1, or plus 2 plus 1, you get 15, which is 1 less than the base, which is 16. So it turns out these 4 numbers right here would be the first digit in your hexadecimal number, and these 4 numbers would be the second digit. So if I wanted to convert this to hexadecimal, I would take 1011, 0101, and I would look at each one separately. So this one is 1, no 2s, and 1 4, so that's what, 5? Did I do that right? Okay. This one would be a 1, a 2, so that's 3, and then no 4s and an 8, so that would be 9. So this number up here is actually 95 when written in hexadecimal form. And you can test it out. You can actually show that it is. So like if I convert it back to decimal now, that would be 5 1s plus 9 16s. 9 times 16, that's, let's see, 50, whoops, 54. And then 9, that'd be 14, so 144. Uh-oh, what did I do wrong? I must have calculated this one wrong up here because this is not looking right. Oh, I 8, 9, 10, 11. How come you didn't correct me? Okay, so 16 times 11, that would be 6 and 1 and 6 and 1, so 176. That changes things a bit. 176 plus 5, there we go, which is 181. Okay, let's say 0, 0, 1, 1, and 1, 1, 1, 0. So there's a binary number, 8 digits. That's 1 byte of information stored on a computer, okay, 8 bits. And so then I can represent that 1 byte either in binary or in hexadecimal. So like when you get error codes on your computer, sometimes it'll have letters and numbers mixed together. Have you ever seen that? So that's because it's displaying them instead of in binary, it's converting all the binary data into hexadecimal for readability. And so then if we take each of these separately now, I'm going to look at them as if they're individual binary numbers. So this would be no ones, a 2, a 4, and an 8. Are you okay with that? And then I go to this one, and even though this is actually the 16s place, for hexadecimal, I can remember that hexadecimal is base 16, which means all of this would have been the first digit of the hexadecimal. All of this then is going to represent the second digit of the hexadecimal. And if I had another 4 digits up here, that would be the third digit of hexadecimal, so on and so forth. So then this would be a 1 and a 2, and then there's no 4s and no 8s. Okay with that? So then this would be 3, and then 12, 14. Now what letter was 14? E. So then 3E would be this binary number written in hexadecimal form. So this is binary, and this is hex. And then to convert it to decimal, you can use either one. Like I could, I can't use these numbers though, because this was when I was converting to hexadecimal. I'd have to treat these as they actually are, which would be 16 and 32. But I'm just going to use this one since it's the shorter number. And so to get decimal, it would be 3 times 16 plus 14 times 1. That's 48. And that's 14. So 52, 62. Okay. So this number really means 62 in our number system, like you would count on your fingers. The reason we use base 10 is because we have 10 fingers. So everybody was basing everything they did on counting on fingers at the very beginning of civilization. There were some civilizations that actually used base 12. It's a superior number system in terms of working with numbers, but it is definitely not it's not what we are accustomed to, so it would really confuse people.